Okay, from today we start at 5 and then ends at 6:15 on both Tuesday and Thursday. Okay. Okay, let's start. So we will start. Last time, we studied some bimodal data and quartile and the box plot and things like that, and this skewed data sets. And then today we studied these paired data. So we consider two different types of data, where the one is height and the other is weight. But those two types of data are linked together. In this case, they belong to the same person, and then they are linked. Okay, and also we obtain, we measure every day's or day temperature and the number of defects in a factory. So suppose a iPhone factory in somewhere, and then as the temperature goes up, the defect rate of this iPhone gets higher and higher, something like that. So in those cases, we have two different types of data, and they are linked together if they belong to the same day. Okay, and in these cases of paired data, we usually interested in their relationships. And we can draw this scatter plot. So we represent one pair of two data types, weight and height, or temperature and the number of defect rate, as a two. We assign two x's on each of these variables, and for each person we can represent it as a point, right? Having this weight and height, and then we can represent a particular person as this point, and in the case of temperature versus the number of defects, and then also every day's record can be represented as a 1 point, and here we are mainly interested in their trends. So roughly they are increasing together, which means if one variable gets larger, and then the other variable gets also larger. So we are interested in knowing this type of data sets. And in this data set, this is called a scatter diagram or scatter plot. And how can you represent this phenomena of getting increased together, or if one increases and the other one decreases? In that case, their relationship gets a little bit opposite, right? So in those cases, the points will have roughly this kind of trend. And how can we quantitatively define this trend as a solid measure? And in order to do that, we consider this centered data. So suppose we have 10 persons' height and weight information, and then we consider its average height and weight, and then we just subtract this average values to each of our observation values. And in that case, it is represented as these notations. And based on a particular the average value or the centered value, if one variable gets higher than that or larger than the center value, and then it means it is like increasing value with respect to the center value. And if the other variable also increases with respect to its own mean value. In this case, we call this situation, they are increasing together, and thus we are saying it as a positive correlation, which means they have relations or correlations, relations between each other. And then positive means if one increases and then the other one also increases. And on the other hand, negatively correlated or negative correlation means if one gets increased and then the other gets decreased. And this positive and negative comes from the fact that there are signs after centering these. Okay, so if one increases, and then this value will be positive with respect to its own center, and then this one is also positive, and then it means they are increasing together, and thus it becomes positive value when considering the multiplication of these two values, right? And then if one increases and then the other one decreases, then their product or their multiplication value will be negative value because they will have a different signs. And then, yeah, more rigorously, this is a correlation coefficient. Correlation coefficient is defined by summing up all these product or multiplication between the two centered variable values. So for one person, we consider this a centered values of these two variable types and then multiply them together. And then for the second person or the next person, we compute that value and then sum them up. Okay? Sum them up. And then we divide it by this value. So it can be viewed as kind of a standard deviation of x only and y only. So yeah, let's look at this one. And then we can distribute this square root on each part. Because it's a product between these two, right? Then taking the square root, we can distribute it to each of these terms, and thus this part will become kind of standard deviation of x and also standard deviation of y. Okay, but let's consider its average value, because when considering the standard deviation, we divided it by n minus 1, right? And also n minus 1. So altogether, if we take the square root, and then it is like dividing by just n minus 1. And then also, we have this kind of term, and then we consider it divided by n minus 1. And so actually in the numerator and the denominator, we divided it by n minus 1, which is the same thing that we did when computing the sample standard deviation or the sample variance. Okay. So this is like the average value of how much they are increasing together or how much they are decreasing together. Okay, and then they are normalized or divided it by the variance or the standard deviation, or how much they are changing for each of these variables. Okay. So this is called a correlation coefficient. Sorry, this is a redundant slide. And this correlation coefficient is usually denoted as R, and it has quite an interesting properties. This correlation coefficient is always between -1 and 1, so it cannot be more than 1, right? And the reason is because so let's make it like larger than 1. Let's try to do so, and then let's try to increase this value. For example, we just multiply x values by maybe 100 times. Okay, so that way we try to make the numerator bigger and bigger, but the same amount of this rate or the multiplier that we applied here is also reflected here. So as x gets increases, the denominator will also increase by the same amount. So that way it cannot increase like into infinite values. So we can we can prove this value is always between -1 and 1. Okay, and in the case of +1, the correlation coefficient is a +1, and then this situation is the case where we draw x and y, and then they are they are aligned along this straight line, but the slope doesn't matter. So in this case, for example, suppose we collected a weight, and also let's consider another data, which is exactly the same value as weight. Okay, we just copy it. Okay, in this case, the correlation coefficient will become 1. But also, suppose we collected the weight, and then let's consider maybe this kind of value, which is kind of approximately representing maybe height or something like that. And if we create the second column by using this exact formula, and then what will be the scatter plot of x and y? It will be something like this, right? So all the points will be on this line. So in this case, the correlation coefficient will be exactly 1. And one thing to note is the slope doesn't actually matter. So whether the slope is 100 or 1 over 10 or maybe 10 or 5, yeah, it doesn't matter. As long as they have a positive slope or positive value of slope, and then the correlation coefficient will always be 1. And then on the other hand, if the correlation coefficient is -1, it means it has this kind of relationship between the two variables, but the second one has the negative sign for its slope. So something like this. In this case, it definitely has this negative sign. Okay, let me just let's look at some example in order to have some intuitive ideas. So in this case, the correlation coefficient is not 1, but close to 1, which is 0.9. So again, the correlation coefficient is ranging between -1 and 1, and as it gets closer and closer to 1, which is the maximum value, and then this kind of scatter plot or scatter diagram will be more like a straight line. But in this case, they are not exactly a straight line, right? So they have some errors with respect to this straight line. So if your data is exactly line on this straight line, and then that's when the correlation coefficient is 1. But here we see a little bit of a noise, right? So they do not exactly follow this line kind of shape. In this case, correlation coefficient gets decreased and gets a smaller value. And so in this case, roughly it has a 0.9. And then what about this? Yeah, so in this case, sorry for the bad drawing, but they seem to have some linear shape, but their width gets bigger than that one. In that case, they are less like this, following this line. So in this case, correlation coefficient will get a smaller value than that one, so it will be like 0.7 or something. And then when will the correlation coefficient be exactly 0? Zero correlation coefficient. In that case, yeah, they don't have any kind of linear relationship. In that case. Okay? So in that case, the correlation coefficient will become 0. And then what about this? In that case, they look like a linear kind of shape, but they are a little bit wide, which means they have a lot of an error. So yeah, they don't have a strong correlation coefficient. And also in this case, the slope will have a negative sign. So correlation coefficient will be minus value. But since it's a little bit thicker than the sharp one, so the absolute value will be smaller than that one. So minus sign comes from the negative slope, but this absolute value of 0.5 comes from the shape. So they are not really narrow or sharp. Okay, and if you have any questions, feel free to let me know. And let's look at the last property of correlation coefficient. Yeah, suppose you collected a person's weight and person's height. So the first person is 70 kilogram and 175 centimeter, and then maybe 65 and 180, and maybe 55 kilogram, and then one maybe 62 or something like that. Okay. So in this case, let's consider the transformation of this weight values into maybe 3x plus 3w plus 5, and this one is also transformed into maybe minus 2. Yeah, let's think about the positive sign, plus 2h minus 3. Okay, so we transform each of the original variables by using some linear simple transformation. And if we go through this transformation, the correlation coefficient doesn't change at all. Okay? So it's really, even though, even after we do this kind of transformation, if we draw these points in a scatter diagram, then they have a linear shape as to whether they have really wide, wide and linear shape, or very narrow, thin linear shape, or clear linear shape. Yeah, those kind of pattern doesn't get influenced by that linear transformation. Okay, so that is about the fourth property. But here they should be they should have the same sign. Okay, so for these signs, in these transformations, they have the same sign, then the sign of a correlation coefficient will not change. But if we change this guy into minus negative 2, in this case, we are actually reversing their kind of patterns. Right? Okay. So in this case, correlation coefficient will get negative value of the original value. So if they are having the same sign, whether they are both positive or negative, then the correlation coefficient will be preserved. So we can, with some derivation or mathematics, we can easily prove these properties. Okay, so in practice, what does this mean? This kind of transformation means. This kind of transformation can be found, for example, when using different units. So for the weight, 60 kilograms, for example, this can be converted into maybe pounds by using some linear transformation. And also Celsius and the Fahrenheit degrees, they have some linear relationship, like, what was it? 5/9 plus 32 or something, right? So 0 degree Celsius is 32 degrees in the Celsius. Maybe it should be minus. But anyway, you know the idea, right? So this is the last slide of this chapter. So this kind of correlation, the strong correlation means they have really a sharp linear relationship. Okay? If one value gets twice bigger than the original value, then the other value will become also twice bigger than its original value. Okay, and so in this case of a high correlation, this kind of correlation may not be the causation. It's really hard to pronunciate, but it is not actually the cause of the other. So let's suppose we collected the year. So we are now living in the year of 2017. Right? 2016, 2014, and so on, and maybe 1997 or something like that. And then let's also collect the life expectancy. How many years on average a person lives. Okay? So due to this medical development, people's lifespan gets longer and longer. Okay? So those two variables, in these cases, the cause or the reason for increase the life expectancy is because this medical development, but not just the fact that time has elapsed or time has been more recent. Okay? So any questions so far? Okay, then let's move on to the chapter 3, the elements of probability. Now we will study some terms. The first one is the sample space. And the definition of it is the set of all the possible outcomes of an experiment. Okay? This is the sample space. So experiment means, so when collecting a person's height and weight, and one experiment means we are picking up one person, okay, out of our work. And then what are all the possible height values when picking up a person randomly? And let's think about simpler example. Suppose our experiment is rolling a dice. So we have a dice, and then we just roll it, and we call one time of this rolling a dice as experiment. In that case, the possible outcome will be from 1 through 6. So the set of all the possible values that we can observe from this random experiment, that is called our sample space, or denoted by S. And then it can be discrete or continuous. So in this case, lifespan of a bulb. So one experiment is picking up a bulb randomly, and then let's think about its lifespan, how many years it survives or it works. And then those values will have this kind of range. Okay. In practice, it may only survive up to maybe 100 years, but let's just consider it can last forever. But it cannot be negative value, right? Because lifespan cannot be like -1 year or something like that. So that way, the sample space can be either discrete or continuous. And then I had some typos in my slide, so I just replaced the slide maybe an hour ago. So if you have an older version, please re-download it. And then let's think about let's study this event, which is denoted by E. And then this E is basically a subset of our sample space. So in the case of rolling a dice, the sample space is 1, 2, 3, 4, 5, 6, right? And then event can be any kind of a subset of that, right? Then maybe 1, 3, 5, which is a subset of our sample space, right? And then maybe just 1, and so on. So all these subset of the entire universe set is called event. And why we call it as an event is because we assume some characteristic or some conditions are involved or are used to obtain the subset. So the first one is the case of picking up the odd number, right? Then maybe this event is picking up the number less than 3, for example. Okay? So that way you can kind of describe, some condition or requirement to satisfy this event. So that's why we call it as kind of event. Okay, then this elementary event is those events that has only one entry or one element in this subset. So this is an element event, but these are not element events. And then union event means, yeah, we just simply take the union of these two events. So the first one is odd numbers, 1, 3, 5. And then the second event is 4, 5, 6, which is more than 3, right? And the union of them, yeah, you can easily compute it. And also we can similarly consider intersection of it, right? That satisfies these two conditions. And also, yeah, complementary event, which is a complementary set. So complementary set is we have a universe here, and then we have a original set here A, and then we call this part as a complement, right? So this is a called a complementary set, and then the this guy's complementary set is of course the even number, right? Okay, and then disjoint or mutually exclusive event, yeah, is such that those two events don't have any intersection. So their intersection is empty set. Okay. Then the probability. Yeah, probability. Yeah, you know the idea of a probability, and yeah, proportion of time, such that the outcome, yeah, contained in E or our event that we defined already. Yeah, we see how many times. I mean, relatively how many times we see the outcome belonging to our event out of the total number of trials or experiments. And then if we do this experiment many times, where n goes to infinity, then the relative frequency will converge to the true probability. Yeah, this is the probability. And these are quite basic things, right? So they are ranging from 0 to 1. Then, yeah, the entire sample space, which is our universe set, or the entire set, can also be a event, because that is also a subset of the sample space or the entire space. So we can of course define this empty event, right? And then also this entire space is also another, its own subset of the entire space. So this is one particular event, and the probability of this event is always 1. And then if our events are mutually exclusive, which means their intersection is nothing. So intersection is empty set. In that case, the probability of union of those events will be just simply taking the summation of each event. Yeah, quite easy, right? Okay, we also know this, right? In case those two events are intersecting, and suppose this event is E and this event is an F, then the union event, and its probability value will be represented by this formula. Okay. Yeah. Then, this is a little bit special notion that we can study in an interesting manner. So odds of an event A is defined by this. So odds are quite a practically useful concept in the world of probability. So this is the ratio between these two events, where the first one is the original event, and then the other one is a complementary event of the original event. Okay? So it's quite simple. So what is the probability of observing 1, 2 out of our dice? It is 1/3, right? In this case, what are the probability of seeing the complementary event ranging from 3 to 6? and then it will be 2 over 3, which is simply 1 over, 1 minus 1 over 3. So in this case, what are the odds? Odds are 1 over 2. Okay, and then what about this? 1, 2, 3, 4. Yeah, this is almost the opposite case. And this is an A or event E, and the complement is 5, 6. And then the odds are 2. Right? And so it's the multiplier or the ratio between these two problems. There is some odds. And unlike the probability value, what is the range or what are the possible ranges of those odd values? So you can go to infinite value, because if the probability of your original event is 0.9999999 something, and then it is divided by 0.00001, right? So it will be even more increased, right? So it's if we draw the so we have 1 here, and if the probability is 0.5, and that's when the odds are what? 1. And it gets large, it gets closer to 1, and then odds will be infinite value. Okay? Then if it gets smaller and smaller, and then it will become like 0. Right? Yeah. So this is an odds. And this is a quite useful concept because suppose you play poker. How many of you know how to play poker? Poker? That many? Texas Hold'em. So in those gambling context or applications, we are very interested in. We are not just interested in the probability value itself, but interested in the probability of how many times, how many times the probability of my winning is compared to the probability of getting defeated. So you are the person 1, and you are competing against person 2 and person 3, and you have the probability of 7 of winning this game, and this guy is 0.2 and 0.1. And in this situation, you can consider this as odd. You can extend this notion of an odd in a way that so if you have 3.5 times bigger the probability of player 2 compared to this guy, you have like a 7 times larger probability than player 3. So that way, this kind of odds is an important concept. Okay. Okay, and then now we consider some experiments composed of a composite trial. So it's a quite simple example. But we flip a coin, and then the possible outcome is head or tail. And then we roll a dice, and then possible outcome is ranging from 1 to 6. And then one experiment is composed of flipping a coin and then rolling a dice. Then we consider all their combinations, right? And so we have head or tail, and we have 1 through 6 as a possible outcome, and then consider all the possible combinations, right? And so the number of possible outcomes in this case, or the sample space, and their number of elements is 2 times 6. Okay. Yeah, it's quite simple, and yeah, this is called a cardinality that I mentioned, I think, yeah, earlier. Yes. Okay, then the permutation and combination. So permutation. Out of n items, we are picking up r items, considering their ordering, right? So in this case, yeah, in the first, yeah, so it is composed of r, yeah, r trials of picking up some elements, and altogether, this is forming one experiment. And what are the possible outcomes, and not the total number of different possible outcomes. So that is this permutation. And then this permutation value is computed by this, right? Because we are picking up our item. So this is the first one, and this is a R's one that we picked up. Okay, and then using the factorial, it can be represented by this. And then also, yeah, we can do this kind of picking up R items without the ordering information. So we basically ignore the orders, and then in this case, yeah, different possible order can have this R factorial numbers. So we further divide it by R factorial. Yeah, so it also is written by this one, NCR, right? But yeah, this is a more common notation, or more international notation. Okay. Yeah, let's think about the conditional probability. Conditional probability is assuming a particular event is already occurred. That has already occurred. And then what is the probability of event? Yeah, another event also has occurred. In this case, it is written by this guy. So this is a event that we assume already occurred, right? And then this is the probability of our interest. And then in this case, you know this, right? And then compactly, this one is just represented as AB. Okay. Then, yeah, since we know, yeah, we assumed already B happened or B occurred, and then in order to have the event A also occurring, we need to consider only the event of the intersection event of these two. And then consider its probability, and then divide it by the original probability of this event B. Yeah, so it's quite easy, right? And then, yeah, from a different perspective, we can consider this intersection probability by imposing some ordering information. So, yeah, those two events have some order. So similar to permutation or combination. So we cannot consider what to choose in the second place without considering the first one. Okay, considering the first one, then the remaining item, we can pick up only from the remaining item. So that will kind of change our situation, right? In this kind of a continuous kind of selection of those numbers. Yeah. So in many cases, those different events has an ordering information. So we consider this ordering information. If A and B are occurring together, then we consider B occurred first, and then consider its probability, and then multiplied by the probability of A occurring, given that B already occurred, or assuming that we know the event B also occurred. And also in this case, we are considering A occurred first, and then consider the probability or conditional probability of event B occurring, given the event A already occurred. Okay, let's look at some example here. So we consider all the possible all the different used cars existing in our world. So there may be 100 used cars. Okay? And then 70 of them, only 70% of them has an airbag. And also out of 100 used cars in total, 40 of them have a CD player. Okay? Then 20% of the used cars actually has both an airbag and the CD player. Okay, and then let's fill this table out. Okay, 20% of them, which means those cars that both have a CD player and the airbag. And where should it be placed? So these are the two different conditions, whether we have an airbag or not, and CD or no CD player. And so we will have 20% here. Okay. And then what will be the total of having an airbag? I mean, the total probability of having an airbag, it is 70%, because the first sentence is saying so. So this should be 70. And then what about this? It should be 50%. And then no airbag means no. Yeah, CD player corresponding to this player, right? Then here we have 20%, and then it should be what? CD player, the probability of it is 40, and it should be 60, and then it should be 10% here. Yep, it's quite easy. And then it's 30%, of course, the total. And then what is the probability of having a CD player given our car has an airbag already? So we only consider those cars that has an airbag, and then only from those subset we compute the probability of seeing the CD player. So in this case, we consider only from here, where those cars that has an airbag. Yep, and then among them, only 20% of them will have airbag and the CD player. So it's 70%, 20% over 70%. So this is how we compute the this conditional probability. Okay. Okay. Then so far, I understand it was quite a little bit boring, because we already know most of them, right? But now let's get a little bit more interesting by studying the Bayes rule. And in order to study this Bayes rule, we first study something called a partitioning of our sample space. So sample space is our entire universe or entire set. And then partitioning is those sets of events. And suppose we have like these three events, these four events, A1, A2. Let's just now forget about the red line and then only focus on these boundaries between A's. And then A1, A2, and let's call this as an A3. And then the remaining part will be A4. So in the case of rolling a dice, A1 will correspond to the set containing only 1, and 2, 3, and maybe 5, and 4, 6. So in this example, those four events will have no intersection, right? So they don't have any overlap between them. Any pair of them will have no overlap. And also, altogether, if we consider the union, okay? If we consider the union, we cover up the entire set that we have for our sample space S. Okay? So this is called a partition. Okay. In this case, let's now consider another type of an event called a B. then E is now representing like this. Then we have 5 and maybe 2 here, and then 3 here, and then maybe 4 here, and then 1 is here, and then this part is 0. So B is another event that is containing 2, 4, 5. Okay. Yep. So yeah, we can consider this kind of event. And we can also consider the probability of this event, B, as the summation of the probability of all these 4 parts. Okay? So if we sum all these 4 parts, and then we can obtain the probability of B. Okay. Yeah. And then, let's just go directly to the example, okay? In order to better understand the base theorem. Okay, so there exists a certain factory, and this factory manufactures some boat, or maybe some iPhone, or some other smartphone. And in this factory, this factory has 3 different manufacturing machines. So each machine will produce the same bolt. Okay? But suppose this machine was bought maybe 5 years ago, and 2 years ago, and 1 year ago. And then in general, the machine will get better and better in terms of its quality. And so it's defect ratio. So for this machine, so if this machine produced 100 bolts, then 5 of them, or 5% of them, will be defective. Okay? And then this machine gets a little bit better, and then if it generated 100 bolts, and then 4 of them will be defective, and 2 of them will be defective from those items, or both manufactured by machine C. Okay, so these are corresponding to these probabilities. And then in this factory, each machine has the portion of the total total manufactured bolt. So suppose we have 100 bolts in total. So this factory manufactures 100 bolts daily on a daily basis. And then every day, machine A produces 25 of them, and then machine B produces 35% of them, and then the third one produces 40% of them. Okay, so our event of A and B and C is defined as the experiment is picking up a bolt. Okay, and then the event of an A is the situation where this randomly chosen bolt was manufactured by the first machine A, and B and C, and their corresponding probabilities will be 25, 35, and 40%. Right? Okay, then now let's think about this probability. Assuming that a bolt was manufactured by the machine A, and then what is the probability of seeing the defective bolt? And this probability will be what? 5%, because in this sentence we can get this kind of information, right? And then if it was manufactured by B, and then the probability of being a defective bolt will be 4%, and this guy will be 2%. Okay, so this is the invariant, or this is the initial situation that we start with. And then the situation that we want to consider is the situation where we reverse the order. This is the defective bolt and also the different manufacturing. So we are interested in the event of seeing the defective bolt. And then we consider the probability of this defective bolt was produced or manufactured by the first machine, the second machine, and the third machine. So this is such a probability that we consider. Okay? Okay, and then this value or this situation is actually a twisted situation because we only know that this bolt is a defective, and we have to consider the probability of this guy was manufactured by the first machine. Okay? But naturally, in terms of the orders of these kind of events occurring, then we first choose one machine among these three different machines, A, B, and C, and then once a particular machine was fixed, and then we can only consider their defective probability. Okay? So that way, choosing the machine is done first, and then whether it's a defective or not is done in the second stage. But we consider the situation where those two events were in a reverse order. So we only know this one is defective, but we consider what is the probability of this defective bolt was produced by the machine A. Okay, and let's think about this figure and then try to understand this example by using this figure. So this is our entire universe or the sample space, and then 20% of them was produced by the machine A and B and C. And the defective event of observing the defective bolt is located here. So this is event B, which means the defective bolt. Okay. So in this case, P of D, or the probability of this part, is of course D was produced by machine A, D was produced by machine B and C. Right? So we can decompose this defective case into these three different cases. Okay. Okay, and then now we consider this conditional probability where we already observed the bolt as a defective one, and then we consider the probability of the manufacturing machine as A for this defective guy. And then in this case, it is represented as this part as a denominator, and then the numerator part is P of A and B. Oops. Okay, again, this part of the probability of observing the defective item. But this defective item can be considered only when first fixing up the manufacturing machine, A, B, or C. And thus, we consider all the three cases, all the possible cases of a manufacturing machine. And then we put it in the denominator because this guy is the probability of observing the defective bolt in total. So that is placed in here, and this part is actually the area of this circle. Okay, the circle is represented by these three parts. Okay, so the sum of those three elements is represented by this. And then, given this situation, we consider the probability of manufacturing machine A actually producing this guy. And so this part is represented by this. Okay. So this part is computed by this formula. We just simply plug those values into this equation. And so here what we did was we actually reversed the natural sequence of these events. Okay? So this is how an intuitive meaning of this. So we have to first consider the manufacturing machine, and then whether the bolt was defective or not. But we actually consider the reverse situation. So we first know that this bolt is defective, and then what is the probability of a particular manufacturing machine given this defective bolt situation. Okay, so and now let's study the formula based on this example. Okay. So the situation is as follows: A1 through AN are partitioning. Okay, we already we already studied the condition or requirement, so that these are the partitioning of our entire sample space. And then, yeah, suppose these probabilities are all positive, and then we consider naturally those events of A1 through AN actually happens or occurs first, and then B is happening in the next place. So that's, suppose this one is a natural order. So yeah, something like this is the probability when thinking of the natural order. So we pick up the manufacturing machine, and then whether it produced defective or defective bolt or not. Okay. Then what we want to represent, or the probability that we want to represent, is as follows. So we have, we know that this event B has actually happened, and then consider the probability of actually the cause of them is the first machine, or A1, for example. Okay? So that way we consider this a reverse kind of probability. And then in this case, what we did was this part. Okay? This part is A cap or cup, no, A cap B plus A B and D plus A C and D, right? So those three were again those three colored parts. Right? Okay, then representing this guy, okay, it is computed as the product or multiplication of the total probability by following the natural order. So we first pick up the machine A and then multiply its conditional probability of producing the defective item from the first machine. Okay, so this guy is 25%. So that's the probability of picking up the bolt manufactured by the first machine. And then what is the probability of manufacturing the defective bolt from the first machine? And that is this guy. So this guy is multiplied by the probability of this guy. Okay, so we can compute this guy, and then in general, for these three different cases, so they are represented as it's a single term by having this summation mark. Okay. So the denominator is following the natural order, and the probability on the left hand side is the probability of following the reverse order. Okay, and so in terms of this order, this guy, which happens first, and their probability distribution between different cases of manufacturing machine. So this is a probability, priori probability, because it happens first. Okay, then this guy, the probability will be considered in a reverse order. So this probability is called a posteriori probability. Okay, but from this equation or this Bayes law or Bayes formula, yeah, we can compute this probability of considering the reverse order by using this kind of formula. Any questions so far? So this kind of priori or posteriori probability, where we consider the natural or reverse order of this kind of event, yeah, is actually widely used in the many practical problems, like in does anyone, have anyone heard about the method called a copy modeling? Copy modeling, or naive Bayes, which is a simple machine learning method. Okay. Suppose you have, suppose, let's think about the document. Okay, document. So, I study math. Okay, then maybe I play Go. In this case, these are two different, their meanings are kind of different. So, this can be considered as like a science or study related topic, and it's a document. And also the bottom part is about like playing, enjoying life and playing some games for fun. Yeah, those kind of types of documents. Right? And then what about other things? So maybe I bought StarCraft, for example. In this case, it can be also classified into this game category and versus study category. Or if you consider the news article, then those news can be classified into the science-related news and politics-related news and the economy-related news and so on, right? And then you can think of generating. So your experiment is observing some sequence of words, okay? Some sequence of words, and then so you picked up one particular news article from the neighbor website without first choosing any categories or something. You just purely randomly chose one news article, and then you think of one experiment. So that document is composed of 10 different words, okay? 10 different words, and then you can consider some probability distribution of science and the game category. And in this case, the science category, the probability of distribution for each word. So for example, the probability of sampling the math word can be relatively high, and then the probability of picking up maybe Go or StarCraft and so on. So they have really low probability. In the case of this science category, but in this case, they will have their own different probability distribution of how likely we can observe a particular word in a given category. So in this case, suppose the game category has different probability distribution of these words. So these are maybe science, and the math, it was a structure, and this was a law and something. Yeah. Okay. Then you actually generate your document, which is a sequence of these words from one of these two probability distributions. Right? But before that, you have to choose particular one between the two, because that's when we can have some specific probability distribution that we can choose our word from. Right? So in this case, we first pick up the pair, and then given that particular distribution, we actually randomly sample our words such as I, happiness, and something like that. That way we can think of two steps, two different stages. So we first pick up topic or category, and then we first later we pick up those words from that probability. Okay. Then, so in this case, we can think of the reverse situation. So we already observed a certain document, but we don't know which category we choose in the first step in order to generate this document. In this case, we observed a certain sentence or the document already because that is already given. So this document is composed of I study math. Okay? And then let's think about the conditional probability of it being science or game, given the same document. In this case, even though that may look like that may look like a cylinder to that one, but we cannot completely ignore the probability of generating this time from that. Right? So that way we can think of this they go exactly the same manner. So there are out of maybe 100 total news articles, suppose we have maybe 70% of news articles related to science and 30% of the news articles related to these are the prior probability, because that is the indicated probability of an event that happened in the first step. Okay, then we consider the event of generating either particular word from that decision and that. Then we can compute the probability of picking up science and those words. This is the first probability, and that is corresponding to something like A1 and this document. And what about the probability of picking up the game and the same document? And this probability. Given the same document, probability of the user copy was science is or is A1 and B. So it is a little bit messy, but we can two cases and add them up. And that way, we create the probability of observing this document without considering all the possible categories. And then we keep the total probability. And then this document also the science category. Okay, so this is exactly the same kind of case. Yeah, and that way, if we, yeah, so in practice, this can be, this can work as some machine learning or artificial intelligence model. So that, given a particular document, what is the topic of this document? Is it science or game-related topic? And so on. So that way, our model can predict the most relevant topic of a given document. Okay, so yeah, this Bayes rule is that much important concept. Okay? And yeah, so that was Bayes rule, and then the next one is independent event. So they are independent if this formula is satisfied, which means the intersection or A cap B, the probability of it is actually the product of these two. Okay, and yeah, let me just write this equation. And is it always true or not? This equation always true or not? So yeah, this is always true. Okay. So yeah, we don't know the natural order, but in principle, purely from this equation or the probability sense, this can be represented by imposing the probability, the sequence of first picking up the B, and then assuming B happened, what is the probability of picking, event A occurring. So this is always true, and also we can freely change the order. So this guy is A and B given A. So these are the same thing, right? And they are always true. But if A and B are independent, then we should satisfy this. Then this guy should be true with this. So these two are the true, but this one is also equal to these two. In this case, when comparing those two, we can conclude that PB is the same as PB given A. Also, if we compare this guy and this, then we can cancel these two, and then the result is PA is equal to PA given B. Okay? So we obtain these two. So intuitively, it means that the fact that B has occurred, that doesn't mean B equals B equals that, and it doesn't change the probability of the original probability. This is the meaning of this equation. And yeah, so this is the independent event situation. And then let's think about this. So okay, in the independent situation, those two should be the same. This is what we write from the previous one. Then let's think about the area of this Venn diagram. So let's just think about the elements are uniformly distributed. The probability will be actually equal to the area of this space. So P of B is A. So this power area is 1, and then the area of this pipe is 0.3 or 30%. And this 30% is actually the same as this guy. And this guy is what? Now our area becomes this one, right? Because it is represented as P of A divided by P of A. And then what is P of A? Is this A. Okay? And then what is P of B? That is this big one, now our main requirement here is this. This is very entire part, but also the green part is also very different of this. So if this ratio is used, and it is used as a constant over the same value, that's when these two events are independent. Okay, so time's up. So okay, that's it for today, and let's meet next this Thursday. 설명을 한 셈인데 약간 그냥 고장이 날 확률이 30% 에서 생산이 돼 머신에가 아닌에서 생산이 돼서 그냥 컨디션 좋아서 나가면서 그렇게 유지가 되면
일어날 확률이 안 일어나는 정의는 소개로 따졌을 때 정의로는 두 개씩만
네, 되게 좋은 질문이고요. 그 부분은 제가 명확하게 하지 못했는데 아즈라는 게 뭐냐면 두 개의 사건이 있을 때의 확률에 각각의 사건이 일어나는 확률의 비율을 아즈라고 그냥 이 확률이 뭐 50%고 나는 이제 50% 그러면 내가 너보다 한 5배 많이 이길 것 같아. 한 번 이길 동안 나는 6배 이길 것 같아. 이 어떤 상대적인 비율을 의미하는 게
일어난다 안 일어난다 될수 없으니까 정의는 실제로는 그게 완벽한 정의 아니고
여러 개일 때는 이제 두 개를 고려했을 때도 이제 아즈라고 네, 조직법이라고 해요. 네.
제한력에 쉼표
쉼표를 썼을 때? 아, 그래요?
장단 수업에서
아, 그래요?
그러면은 합집합은
합집합은 뭐 특별하게 없고 그냥 컵을 썼을 때 유니언 비용 컵을
그리고 약간 이거 사용이라고
혹시
이게 정확하게 이해 안 가는데 그러니까 이게 그냥 중요한 부분인가요? 이 AK는 원래 정해져 있는 거 이거는 B가 일어나서 같이 변한다는 거예요?
네, 그러니까 둘 다 그러니까 무슨 설명을 드리죠? 둘 다 A들에 대한 프로블럼을 따지고요. A들에 대한 프로블럼을 따지는데 원래는 A가 뭔가 고정이 되고 나서 B가 일어나는 게 정상인데 B가 뭔지도 모르지만 뭐가 나오는지 모른 채로 그냥 A들이 각각이 얼만큼 일어날지에 대한 확률 분포가 이제 쌓여 있죠. 그 다음에 포시에어는 뭐냐면 B가 뭔가 그러니까 A들이 누군가를 정해줬어요. 이게 그러니까 A1이 될 수 있다 아니면 내가 A1에 대한 프로블럼을 드릴 수가 있어요. 굉장히 매니페이션에서 A에서 생성되는 확률이 25%. 그거는 아무 정보도 없을 때에 A라는 것에서 생산될 어떤 확률, A라는 이벤트의 확률이 25%라는 거고요. 근데 우리가 A, B, C 이렇게 A 포함해서 다른 것들이 중에 하나가 일어났고 그 다음에 뭔가 일어나는데 이게 이제 고장에 해당합니다.
그래서 그 고장이 일어났을 때, 그러니까 그 이후에 일어난 사건이 뭔가 정보로 주어졌을 때에, 그런 부가적인 정보가 주어졌을 때에 과연 그러면 A1의 확률, 그러니까 A의 확률이, 그러니까 머신 A가 될 확률이 바로 포스트이 됩니다. 그러니까 그 이후에 포스트라는 그러니까 이게 약간 뒤바뀐 거예요. 그러니까 사건이 B가 혹은 이제 디펙티브냐 아니냐가 더 뒤에 일어나는 건데, 제가 일단 일어났다라는 게 이제 전제가 된 상태에서 거꾸로 이제 A가 뭐일지를 추정하는 주어진 어떤 자연스러운 이벤트가 일어나는 시퀀스가 역전이 되는 거죠.